Hi, my name is Troy Baietto. I'm a solutions architect with A&M. And today we're going to talk about a couple of technologies within Wi-Fi 6 that create the efficiencies and speed required to do some of the things that we want to do in today's world. So some of the things like getting the speed required for augmented reality, for 8K streaming, for video conferencing, things like that. But also the efficiencies to have the kinds of densities that we're seeing within client bases, where we don't want to put an access point on every single ceiling tile. But we need to account for the explosion in Wi-Fi devices. So today we're going to dive into two technologies, which is a very small sample of the things that allow us to do this within Wi-Fi 6. The first is quadrature amplitude modulation, and the other one is orthogonal frequency division multiplexing, or in Wi-Fi 6, multiple access. So we'll get started with quadrature amplitude modulation. It's a mouthful. So we'll start with just a signal, right? So the best way to think of any wireless signal or radio frequency signal is Morse code. That was the very basic signal that's not modulated at all. So if we want to write my name, which is Troy, the Morse code for that would be dot, dit, dot, dit, dot, 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 dit, dot, dot, right? It's one dimension. It's very monotone, like my science teacher in 8th grade. So what do we want to do? So you can't get a lot of data in this. This takes a lot of RF to just spell my name. So one of the things that folks did is they started to modulate the radio frequency. One of the best ways to do that, if you wanted to send a signal with some depth, right, like this one, which might be somebody speaking, is to modulate the amplitude or the up and downs of the power. So we would modulate it down and then modulate it like that. I tried to keep the distance between these two the same because this is the frequency and this is the amplitude. So we're modulating the amplitude in order to change the signal. And this gives us what's known as AM, or amplitude modulation, which is popular radio, says my grandpa. So now what we want to do is we want to do something even more. This gives it some depth. It makes it from a one-dimensional thing to a more two-dimensional, and allows us to encode a little bit of data in that we could put voice and music and things like that. So we have our news radio. Now, quadrature amplitude modulation takes things a step further, because what we want to do is we want to be able to send datagrams. Now, what we're going to do is we're going to draw a Cartesian plane. And when we talk about quadrature, this is the quad, right? So there's 4 areas here. This is the phase, and we'll call this the time, okay? Or this is actually the amplitude. And so what we're going to do is we're going to put a symbol in each one. So we'll say each of these symbols is some data, okay? And what we're going to do is we're going to have this is the point at which we're going to sample the data. And it's like a radar. It's going to turn like that, right? And it's going to turn. And so at this phase, so at this 215-ish degree angle, and at this moment of time, we're going to read this symbol. Now, so this is quadrature amplitude modulation, or as some people call it, QAMP. Now, in Wi-Fi A, in 802.11a, G, and N, we had 64-bit QAM, so this was a G, N, right? And this was 6 bits per symbol. So each of these symbols represented 6 bits. In 802.11 AC, we got to 256-bit, or which allowed us to do 8 bits per symbol, but it also increased the density. So now we had more dots and more spots on the graph to sample this phase. Now in Wi-Fi 6 or 802.11 AX, we have so AX 1024 QAM, which is 10 bits per symbol, right? And you can imagine with that kind of density within the radio symbol, we're now getting more than just dots and dits and things like that in order to spell a name. We're getting, with every turn of this phase radar, we're getting a ton of data out of it, and that gives us 10 bits per symbol, this is what allows in one radio Wi-Fi 6 to get to 1.2 gigabits per second. And this is also why you see vendors out there who put 8 radios, right, on their access points get over 10 gigabits per second. Right, so this gives us the speed required, and this is the technology that's allowing us to go faster and faster and faster, even though the airwaves are still the same. It's the same reason why we're getting faster and faster and faster. Ethernet, even though it's still just copper cabling. It's the way that we're modulating. It's the way that we're putting science behind packing more data into it, right? So this again is something that helps us with Wi-Fi speeds. So this is what gives you that 8K video. This is what gives you that augmented reality capabilities within Wi-Fi. So now we're going to talk a little bit about orthogonal frequency division multiplexing, which was the sort of AO2.11ac technology, and how orthogonal frequency division multi-access, which is the Wi-Fi 6, differs. And what OFDM and OFDMA do is gives us the efficiencies and density for a ton of clients. And I'll show you why. So we talked about, modulating a signal. And you can have one signal basically per channel. And in Wi-Fi, there's multiple channels. Let's say that we have a channel, and if you look at a wireless analyzer, it would look something like that, right? So we'll say that this channel width is 20 megahertz, right? So in the old technologies, you'd have a 20 megahertz channel, and you'd be able to transfer 1 frame of data per channel per user at one given time, right? The radio can only do that because if radios collide, they cancel each other out. So you don't want to do that. So what OFDM did, or orthogonal frequency division multiplexing did, was it allowed us to break this channel into what's called carriers, right? So the cool thing about that is now we can, in a single, we can break the single lane of Wi-Fi transmission into multiple lanes. And I'm going to do my best to draw trucks to symbolize this. So this is the cargo of those trucks. Now remember, before OFDMA, we can only have one truck at a time. Now let me draw the part I suck at, because I just pretend I'm drawing shoes, and that's how I practiced for this. I had my kids help me. Make sure we have the wheels in. So now with OFDM, with orthogonal frequency division multiplexing, we're actually able to take this single lane highway and break it up into carriers or trucks, right? So now these trucks have their own lanes, which is good, right? Because now I can put some data in this truck, some data in this truck, and some data in this truck. And that's great. It gives us some efficiencies. The problem with this is over 80% of wireless frames are less than 370 bytes, right? This is the reality of Wi-Fi. We don't have the idea of jumbo frames in Wi-Fi. There just isn't enough airtime for it, right? So we break things up, especially with real-time data, especially with voice, especially with video, all the stuff that's blowing up, right? So a lot of times when you have 80% of your wireless frames less than 370 bytes, these trucks aren't very full. So where OFDM gave us some efficiency, it still lacked because there was still a lot of empty space. So what multiple access allows us to do is break it into subcarriers, right? So this allowed us finally to not only put more data, but more than one user as well. Because the other thing that made OFDM a little less efficient is if you missed your window to get on a truck, you had to wait for all of the trucks to leave and a new set of trucks to show up. With OFDMA, if you want to transmit, there's always a truck there with a little bit of space, right? So with orthogonal frequency division multiple access, we're allowed much more efficiency, right? And this is why we're allowed to have so much density within Wi-Fi 6 without putting a ton of access points all over the place. These technologies continue to evolve. And again, these two technologies here are just a small sample of what makes Wi-Fi 6 capable of doing the things that we're seeing done. There's more. There's MIMO, there's Wi-Fi 6E, where we introduced the 6 gigahertz range, but we'll save that for another session. I hope this helped understand both QAM and OFDM and OFDMA. We'll see you next time.